In 1964, Stephen H. Dole and Isaac Asimov got together and wrote a cute little book entitled, Planets for Man. Chapter 7. Star Hopping. Detecting a planet. We may be able to calculate from our armchairs the probability of a given star possessing a habitable planet in orbit around it, but under what conditions would we be certain of it one way or the other? Naturally, a space flight to the star in question would tell us, but need we actually travel all the way there? In other words, at what distance can it be ascertained that a specific star actually possesses an apparently habitable planet? And how closely must we approach a planet in order to be sure that it is indeed habitable? As we know from experience, it is not easy to tell a great deal about a planet even from a vantage point within the stellar system of which it forms a part. There are still many unanswered questions, for instance about Venus and Mars, although the Earth periodically comes closer to them than 30 and 40 million miles respectively. To be sure, this is not grounds for complete pessimism. Much of the difficulty with respect to our neighbor planets lies in the fact that we are looking at them through our own radiation-absorbing and image-distorting atmosphere. Undoubtedly, we will learn a great deal more about the planets of our own system, even before we actually visit them, once telescopes of merely moderate size are put into operation in space above the atmosphere. Imagine then that we are on an exploratory mission on a spaceship that is approaching a star. We have telescopes up to 60 inches in diameter, sensitive radio receivers, and other necessary equipment. We would like to make a decision at the earliest possible moment whether to continue going toward the star or whether to break off and return to base or head for a second objective. Let us say that our first decision will be based on whether the star has a planet orbiting within an ecosphere. If it has such a planet, we will proceed. If we can say that it definitely does not, we will break off. To see what this implies, let us consider a star like our Sun, about which planets like Jupiter and the Earth circle at distances equal to those that hold true in our solar system. At what distance could we detect the Jupiter-like planet, and at what distance the Earth-like planet? In a way, we can detect Jupiter-like planets even at distances of a number of light years. In recent years we have actually detected 3 planets of this sort without moving from the surface of the Earth. In 1948, the proper motion of the binary 61 Cygnus system showed irregularities that could be due only to the presence of a third non-luminous object, 61 Cygnus c. From the size of the irregularities of motion, it was deduced that 61 Cygnus c had a mass only 0.008 times that of the Sun, and therefore 8 times that of Jupiter. This new body 61 Cygnus c is larger than any planet in our solar system. In fact, it is large enough to be in the planet-to-star transition range, which alone would make it a fascinating object for close-range study for anyone interested in general planetology. If we assume that it is a giant planet rather than a tiny star, then it has the distinction of being the first planetary body to be discovered outside our solar system. In 1960, similar studies showed that LALON 21185a had an invisible companion, LALON 21185b. The latter body, like 61 Cygnus c, is about 8 times as massive as Jupiter. Finally, in 1963, a smaller body, one that can only be a planet, was found to be circling Barnard's star. This new discovery, Barnard's star b, is estimated to be only 1.5 times the mass of Jupiter. Barnard's star A is only 6 light-years from us, and LALON 21185a is only 8 light-years distant. They are the second and third closest star systems respectively, and only the Alpha Centauri system is closer. The fact that 2 out of 3 of the nearest star systems have already been found to possess planetary bodies, despite the handicap of observations from great distances, is strong evidence for the contemporary feeling that all stars have non-luminous companions. To be sure, the planets discovered cannot possibly be habitable, and indeed none of the stars involved could have habitable planets, except for possible satellite-maintained planets around either 61 Cygni A or 61 Cygni B, but what is true for these stars is also true for stars better suited for habitable planets. The detection of planets by means of their gravitational effects upon their primaries, while the only route open to us now, would be impractical for our exploring space travelers. Discovery through gravitational effects requires many years of meticulous observation. We must resolve the problem more quickly than that, and the most practical way of doing so is actually to see the planet. When viewing the universe through our atmosphere, it is very difficult to observe a faint object close to a much brighter object. This is because the light from the brighter object interferes, and because the poor seeing through our shifting wavering atmosphere prevents us from obtaining the best results that in theory our large telescopes could give us. A telescope employed in space, however, is free of atmospheric interference and would be able to attain its theoretical best in detecting and separating closely spaced objects of equal brightness. Also, faint objects close to brighter ones might be picked up through use of special techniques such as hiding the image of the brighter object with a knife edge. It seems that such techniques could be used to reveal a dim body within 2 seconds of arc of a bright one, provided the apparent magnitude of the dim body was magnitude plus 18 or brighter, since a 60-inch telescope cannot detect anything dimmer than a magnitude of plus 18. If we assume that a planet like Jupiter is viewed by a spaceship that is approaching from an angle that makes it possible to view the planet as widely separated from its primary as possible, the planet would then be half illuminated to the eye. The maximum separation of the planet and its primary, assuming the separation to be that between Jupiter and the Sun, would be 2 seconds of arc at a distance of 8.55 light-years. This is twice the distance that separates us from the Alpha Centauri system. However, a Jupiter-like planet could be seen at that distance only if it had attained the necessary minimum brightness, and this it certainly does not manage at a distance of 8.55 light-years. Assuming an albedo of 0.4 and an image that is half illuminated, its magnitude would not reach the necessary plus 18 until a distance of 0.43 light-years is reached. This is a distance of 2.5 trillion miles, or 600 times the distance of Pluto from the Sun. Thus it is the apparent magnitude and not the apparent separation from its primary that sets the maximum distance for optical detection. At a distance of 0.43 light-years, the separation of planet and primary would be about 37 seconds of arc. Seeing the planet as a mere speck of light would still not be enough, however. It would be embedded in a field or background containing so many distant stars of like magnitude that each such object would have to be analyzed spectroscopically to discriminate between the planet and the surrounding stars, or else repeated photographs would have to be taken to detect the motion of the planet against the background of motionless stars. Much too would depend on the tilt of the system with respect to the line of approach. The most favorable approach line would be at right angles to the plane of the planetary orbit, for then the planet would always be seen at maximum distance from its primary. Under less favorable conditions of approach, with the planet more or less between us and the star, the apparent distance between the two would be considerably less than maximum much of the time, and detection could be made only at distances much shorter than 0.43 light-years. All, in case of continuing doubt, it might be necessary to come in close enough to see the Jupiter-like planet as a disk. Such a disk would be discernible in a 60-inch telescope as an object 2 seconds of arc in diameter at about 90 AU, 8.4 billion miles, or somewhat more than twice the distance of Pluto from the Sun. Similar difficulties of a more extreme type would prevail in the detection of a habitable Earth-like planet considerably smaller than Jupiter and considerably closer to its primary. Assuming an Earth-like albedo of 0.36 and maximum separation, such a planet would be separated from its primary by an apparent distance of 2 seconds of arc at a distance of 1.7 light-years, or about a third of the way to the Alpha Centauri system. However, the Earth's reflected light would be detectable only at 1/10 that distance, 0.17 light-years, or just about 1 trillion miles. An Earth-like body would be perceptible as an actual disk of 2 seconds of arc in diameter at a distance of about 7.6 AU, 700 million miles, or not quite the distance between Saturn and the Sun. We would not then be able to detect the presence of an Earth-like planet, under the present assumptions, until we had approached the target system to within 1/6 of a light-year. Unfavorable indications such as the presence of a giant planet in such a position as to prevent the orbiting of a habitable planet within an ecosphere might be detected earlier. Detecting planetary details. Once an approach to within 1/6 of a light-year has been made and an Earth-like possibly habitable planet has been detected, one must approach even more closely to ascertain habitability. If no such planet is detected, of course, after so close an approach, it may pay the explorers to veer away. As one continues the approach, various properties will be observed that will contribute to a decision concerning its habitability beyond that of the mere existence of a planet of the proper size within an ecosphere. Radio waves, for instance, might be detected of a form that would bespeak not only a habitable planet but one with intelligent life. Radio waves in the broadcast band, 535 to 1605 kilocycles, originating on Earth, do not penetrate the Earth's ionosphere very effectively, and most of the energy is refracted and returned to the Earth. It is only the very high-frequency radio waves, those with frequencies of more than 30,000 kilocycles or 30 megacycles, that would be detectable in space. In the very high-frequency bands, some of the most powerful earthly sources are the ballistic missile early warning system radar stations broadcasting signals of a frequency of about 400 megacycles. Taking the peak power level as about 1 megawatt, 1 million watts, and assuming that the natural galactic noise at the receiver is that produced by objects at room temperature, the signals from ballistic missile early warning systems transmitters might be detected at a distance of 10 billion miles, or 2.5 times the distance of Pluto from the Sun. Such a situation would not be very likely, however, since we do not expect to find habitable planets with intelligent life, as opposed simply to life, except at rare intervals. Still, planets may emit radio signals even in the absence of intelligence. Certain kinds of natural radio noise may be characteristic of planets that, like the Earth, have numerous thunderstorms and lightning flashes occurring in their atmospheres at all times. There might be a recognizable pattern to such radio noise that would at least serve as an indicator of a planet with an atmosphere, though not necessarily a breathable one, of course. What fraction of this noise would leak out and be detectable in space at a distance from the source is not known with any degree of certainty. Characteristic spectral absorption lines due to oxygen or water vapor might be detected as soon as a planetary image is obtained. The detection of these lines can be accomplished only with great difficulty when looking through the Earth's atmosphere, because the prevalence of oxygen, water vapor and other absorbing gases in our atmosphere confuses the issue, but such detection would be quite feasible from space. Estimates of the approximate distances at which important surface features of the Earth could be identified from space are oceans at about 7 AU, 650 million miles, forests at about 3 AU, 280 million miles, and large cities at about 5 million miles under good viewing conditions. Closer approaches and very clear atmospheres would be needed in order to identify as artificial structures such conspicuous works of man as canals, dams, bridges, airfields, railroads, and so on. Generally speaking, then, we will not be able to explore the stars cheaply by taking a quick look from a distance. A system will have to be approached to within 1/6 of a light-year before it can be definitely determined to have no habitable planet, although certain negative indications might be obtained while the exploring party is still as far away as 1/3 to 1/2 of a light-year. This means that even the nearest star system cannot be eliminated until 90 to 95% of the trip there has been completed. For more distant stars, the portion of the trip that must be completed is higher still. Once the presence of a habitable planet is seen to be possible, a closer approach to within 1 million miles or so is required in order to be fairly certain of habitability. To be absolutely certain necessitates a landing on its surface and direct investigation of such matters as its atmosphere and surface conditions. Any indication that a planet is already inhabited by intelligent creatures would signal the need for proceeding with the utmost caution. In fact, before a manned landing is made on any likely-looking planet, it would be desirable to study the planet thoroughly from a distant orbit around it for a protracted period of time, to send sampling probes into its atmosphere, and to send surveillance instruments down to the surface. Contacts with alien intelligence should be made most circumspectly, not only as insurance against unknown factors but also to avoid any disruptive effects on the local population produced by encountering a vastly different cultural system. After prolonged study of the situation, a decision would have to be made whether to make overt contact or to depart without giving the inhabitants any evidence of the visitation. Interstellar flight. As man's ability to accelerate payloads to higher and higher velocities increases, a point may eventually be reached when interstellar flight can begin to be considered feasible, and when the type of exploration that we have been assuming in this chapter will really enter the realm of the possible. At the present time we have barely reached the point in technology where we could design a rocket vehicle capable of sending a small package completely out of the solar system. Its velocity at a distance equivalent to the orbit of Pluto would be very small relative to the speed of light, however perhaps not more than 1/10,000th that speed, 18.6 miles per second, or 67,000 miles per hour. Consequently, trips to even the closest stars would take many thousands of years, and it would not be worthwhile even to consider such a slow trip. But if one has confidence in man's ability to learn, a confidence justified by looking back at the accelerating pace of technical progress over the past 400 years, then one may be optimistic about the future feasibility of flights over interstellar distances. Flights at velocities that are large fractions of the velocity of light do not violate any of the known laws of physics, although the expenditures of energy needed for accelerating to such velocities are enormous. It is to be hoped despite that flights at such high velocities will someday become practical. Once we have a capability for sending small packages over interstellar distances at velocities of the order of 1/10 the speed of light or higher, then we could consider sending unmanned probes to the vicinity of the nearest promising candidate stars to report back to Earth on the prevailing conditions. It would take years for radio waves or any other form of communication to make their way back to the Earth, but that cannot be helped. Favorable reports could be followed by manned expeditions to those systems, showing the most promise in the light of our then greatly enhanced knowledge of astrophysics and general planetology. The requirements for speed and ingenuity will depend on how far away the nearest promising star candidate happens to be and on how determined people are to make the trip. If one is willing to spend 20 years en route, then trips to stars 4 light-years away could be made at 1/5 the speed of light, 37,000 miles per second. Trips to stars 10 light-years away could be made at 1/2 the speed of light, 93,000 miles per second. Trips to stars 15 light-years away could be made at 3/4 the speed of light, 140,000 miles per second, and so on. At velocities approaching the speed of light, moreover, relativistic time contractions become quite evident, so that for a particular round trip considerably less time would seem to have elapsed for the traveler himself than for an earthbound observer. Thus enormous distances, from the viewpoint of the earthbound observer, could be traversed in 20 years, from the standpoint of the traveler, if velocities very close to the speed of light are attainable. There is, it should be pointed out, a complication in the optical detection of objects in space when the observer is moving at near light velocities. At such velocities the light from the star being approached seems to shorten considerably in wavelength and becomes quite a bit more blue. In other words, the star appears to be hotter than it actually is. On the other hand, when one is moving away from a star at such velocities, its light seems to shift toward the red end of the spectrum and the star appears to be cooler than it is. At very high velocities a black spot will appear in the directly forward direction, since all the visually detectable radiation from the stars in that part of the field of view would be shifted into the ultraviolet. Another black spot will appear in the directly backward direction, since all the visually detectable radiation from the stars in that sector would be shifted into the infrared. Between the two black spots the stars will range in color from blue to red as one progresses forward to backward. In the visual black spots, however, the stars will still be detectable with instruments. These effects would start to become apparent to the casual observer at velocities of about 1/20th the velocity of light, 9,300 miles per second, while the black spots would appear at velocities of about 1/2 the speed of light, 93,000 miles per second. Even at vehicle velocities much lower than that of light, however, the duration of the trip might possibly be shortened, for the traveler, through the development of hibernation techniques or their equivalent. The traveler might then sleep the years away as his ship approached its destination. Kinds of habitable planets. Once interstellar flight is developed and stars with habitable planets are reached, unlooked for varieties of experience should open to the human race. To be sure, the most common kind of habitable planet, if the ideas developed in this book are essentially correct, should be similar to the Earth in many respects. The one mild peculiarity of the Earth is its rather large natural satellite. The typical habitable planet should be of much the same mass as the Earth, although perhaps a bit smaller on the average, and it should have a similar atmosphere, a similar night-day cycle, a sun of similar size and appearance, a mild inclination to its equator and a moderate eccentricity to its orbit. Seasons should be part of the common experience of the inhabitants, as well as oceans, beaches, breezes, clouds, rain, snow, thunder, lightning, volcanoes, earthquakes, rainbows, sunsets, starry nights, blue skies, deserts, mountains, rivers, glaciers, and polar ice caps. In short, most of the physical and meteorological phenomena with which we are familiar should also be known on most other habitable planets, although always with enough difference in detail to make each planet a fascinating experience. When it comes to the living things indigenous to the planets, of course these might differ widely depending on the precise course that evolution happened to take in each special circumstance. Even so, on each planet one would expect to find organisms carrying on photosynthesis and creatures capable of invading practically every conceivable comer of the environment: marine forms, freshwater creatures, land creatures, aerial forms, cave organisms, and so on. In spite of differences in detail, certain basic kinds of life forms would be expected to display some common characteristics. Thus, fast-swimming marine forms would be streamlined, land animals would typically have legs, and fast-moving aerial forms would have wings. There must of necessity be autotrophs, life forms that use only inorganic nutrients, and one would also expect to find heterotrophs, life forms that use autotrophs or other heterotrophs for food. On no other planet, however, would we expect to find any of the actual phyla of plants or animals with which we are familiar on the surface of the Earth. From the smallest virus to the largest whale, the earthly life forms are unique products of the Earth. Each planet on which living things have evolved must have its own peculiar classification of organisms, and this in itself should present the human race in general, and biologists in particular, with endless realms of new wonder and experience. But in addition to these typical Earth-like habitable planets, there should also be many unusual and rarer kinds among the 600 million habitable planets that we have estimated to exist in our galaxy. Some of the special types are easily imagined. A satellite planet would be a habitable planet in orbit around a gas giant like Jupiter, the two revolving about a primary. The rotation of the habitable planet would be stopped with respect to the companion, but rotating with respect to the primary. Such a planet would have unusual cycles of light and dark on the side facing its companion, for the nights would be dominated by the presence of an extremely large and luminous moon. The side away from the companion would have more normal day-night cycles. Then 2 eclipses of the primary would occur every day unless the planet's orbit about its companion was at a marked angle to that of the companion's orbit about the primary. Twin planets revolving about a common center of mass would have their rotation stopped with respect to each other. It would be interesting to speculate on the intellectual development of a life form on one planet of such a pair. With another planet close and large, with clouds, oceans, and continents clear to the naked eye, could any egocentric philosophy of the universe develop? Would the urge to reach the companion hasten technological progress? We can ask but can offer no answer. A planet with 2 suns would be a habitable planet in orbit around 2 stars that are very close to each other. Close binaries, separated by a few million miles say, would produce a somewhat complicated sunrise and sunset pattern for a habitable planet in orbit around them, and an interesting variation in light intensity as the stars eclipsed each other, but otherwise they would not necessarily greatly affect conditions on the surface of the planet. A planet in a widely separated binary system rotating about 1 star in that system would have very bright nights during those parts of the year when it was passing between the 2 stars, and normal dark nights only when the companion as well as the primary was beneath the horizon. From a habitable planet in orbit around Alpha Centauri A, for example, Alpha Centauri B would seem to be a very bright star-like object that would range in magnitude from -18 to -20 depending on whether the 2 stars were at a pastron or periastron. Alpha Centauri B at its brightest would appear over 2 million times as bright as Venus appears to us, and nearly 1,500 times as bright as our full moon. This type of planet and the type mentioned immediately preceding may not be particularly rare. A planet with very high equatorial inclination must lie within a narrow range of distances from the primary to be habitable at all, and even then only a small fraction of its surface might be habitable. A planet with an equatorial inclination of 75 degrees even at optimal distance from its primary would be habitable only between latitudes 14 degrees north and 14 degrees south. On Earth this would represent a belt 2,000 miles wide centered on the equator. Higher latitudes would be excessively cold during the winter season and excessively hot in the summer season. A planet with two habitable belts would most likely be found among planets having low equatorial inclinations but orbiting near the inner edge of the ecosphere. Such planets are excessively hot near the equator, hence the habitable regions would be in the intermediate or high latitudes only. A planet having the same equatorial inclination as the Earth, 23.5 degrees, but orbiting at a distance from its primary such that it received 30% more illuminance than the Earth would be habitable only between latitudes 51 degrees to 66 degrees north and south. Such belts on the Earth would include the Soviet Union, Canada, the British Isles, Scandinavia and parts of Germany and Poland in the north and nothing in the south but the extreme tip of South America. With the wide belt from 51 degrees north to 51 degrees south intolerably hot and perhaps impassable to many life forms, it is quite probable that land life forms would evolve more or less independently in the two regions. Marine life and some aerial forms might migrate between the two, but land migrations would be fairly effectively stopped by a heat barrier consisting mainly of deserts, possibly with small pockets of habitable territory on mountain plateaus. Habitable planets with rings are another possibility. There are many unknowns associated with the origin and composition of the beautiful ring system of Saturn, and it is quite probable that massive oblate planets are more likely to possess rings than are planets in the habitable class. Nevertheless, it is reasonable to suppose that a few habitable planets may also have flat equatorial rings inside their Roche limits, although these rings would probably not be as thick with debris as are the rings of Saturn. Other special types of habitable planets may also exist. Since oceans are believed to be products of volcanic activity, and since such activity increases possibly with the mass of a planet, it may be that high G planets are largely oceanic and low G planets are largely dry land. Planets with more extensive oceans than the Earth, those having say 90% oceans and 10% dry land, might well have quite widely separated continents with no land bridges. Fairly independent evolutionary courses might be followed by the land life forms so that each continent would be virtually a world to itself, biologically speaking. On the other hand, planets having substantially less oceanic water than the Earth might well have non-interconnecting oceans, large lakes really, with isolated forms of marine life undergoing separate evolutions. An oceanic planet with the same irradiance as the Earth would have more equable temperatures, so there would be an absence of polar ice caps. A dry land planet in the absence of worldwide oceanic circulation would have extreme temperatures. A high fraction of the land surface probably would be desert, and the main habitable regions would tend to be close to the landlocked seas. Our Sun is situated in a fairly sparsely populated section of the galaxy in one of the spiral arms well out toward the edge of the disk. Our night sky therefore is relatively lightly sprinkled with stars in comparison with what would be seen from planets located in certain other positions in the galaxy. Something like 2,500 stars brighter than magnitude 6.5 are visible to the naked eye from a given spot on the Earth on a clear night. Much more spectacular night skies would be seen from habitable planets located in globular clusters or near the center of the galaxy. It has been estimated that about 2 million stars of magnitudes brighter than 6.5 would exist above the horizon of a habitable planet located near the galactic center. The starlight in such a sky would be roughly equal to the light of the full moon as seen from the Earth. The scattered light in such a sky would, however, prevent one from seeing any but the brightest stars. Stars fainter than perhaps magnitude 2.5 could not be seen at all against the overall luminosity of the night sky. Even so, the number of stars brighter than this limiting magnitude would number approximately 30,000, or more than 10 times as many as we can see on the darkest night. On the other hand, habitable planets around stars embedded in some of the dusty regions, dark nebulae, of the galaxy might have almost no stars at all in their night skies. And habitable planets around stars at the very edge of the galaxy would have stars in one half of the celestial sphere but none in the other half. On the starry side, the galaxy as a whole would be visible as a Milky Way with structure, a foreshortened vision of a spiral galactic whirlpool. The only lights in the night sky looking away from the galaxy, apart from local planets and a very occasional star, would come from extragalactic nebulae or distant island universes, only a few of which, like the Large and Small Magellanic Clouds or the Great Nebula in Andromeda, would be faintly visible to the naked eye. Man in new environments. And if new habitable planets offer new kinds of environments for man, man may well respond by developing new varieties of himself. Human beings, together with all other life forms on the Earth, are very well adapted to what we think of as a normal environment. Although the normal environments of the Eskimos, of the Australian Aborigines, of the Pygmies of Africa, and of the Indians of the high Andes are quite different from one another, they all fall into a fairly narrow range when viewed from the standpoint of possible variations among the different planets. All of the people mentioned above occupy more or less marginal ecological niches, but they have become adjusted to them gradually. This adjustment probably has come about through many generations of selection for individuals who could tolerate exceptionally well the environmental extremes of temperatures, the dietary limitations, the dryness, or the low oxygen partial pressure, as the case happened to be. Colonizers of other planets will encounter even more varied environmental conditions than those existing on the Earth's surface. The transitions, however, unlike those made by peoples in the past history of the Earth, will of necessity be abrupt rather than gradual. The colonizers will of course have the advantages of a very high level of technology to assist them in making the transitions. Even so, unless close contact is maintained with the population pool of the Earth, very profound genetic shifts will undoubtedly occur in a relatively short time if the environmental conditions are markedly different from those of the Earth. In future times, if interstellar trips become possible, there may be circumstances under which an expedition locates a habitable planet and then through accident or design is cut off from communication with the rest of humanity for several hundred years. Imagine such a colony marooned on a 1.5G planet, for instance. Assuming that the colony is able to survive and multiply, there would inevitably be a premium on muscular strength, short reaction times, and accurate judgment in moving about. There would also be a premium on strong internal constitutions. All this follows from the fact that because of the high surface gravity, so many aspects of life would become more crucial. Accidental falls would be more dangerous, more likely to be fatal or crippling. Sprains, strained muscles, hemorrhoids, fallen internal organs, back, foot and leg ailments, varicose veins, and certain difficulties of pregnancy would all be more prevalent than in the gentler low-G environment of the Earth. Thus there would be an inexorable selection pressure continually favoring those individuals best equipped to deal with the problems of a high gravitational force. After a number of generations under these environmental conditions, the population would change in appearance. Experiments with chickens have shown that animals raised under high gravity exhibit an increase in relative heart and leg sizes, and these observations might also apply to human beings. Those humans best able to thrive under high G conditions would probably tend to have shorter arms and legs. They would be more compactly constructed and would have heavier bones than any population normally found on the Earth. Because of the constant drag of gravity, human beings on such a planet would tend to have better muscular development and less unsupported external fatty tissue, so that standards of attractiveness would change. Since it would be an advantage during pregnancy to have small babies rather than large ones, the average height of the adult population would probably tend to decrease to some optimal level. Again, since objects fall much faster when surface gravity is high, selection would also tend to favor people with unusually rapid muscular reactions. If isolation is continued for a long enough period of time, there would inevitably be various kinds of minor genetic drifts in unpredictable directions. If continued enough, genetic changes would accumulate so that the isolated population would no longer be able to interbreed with the population of the Earth when the members of the two planets again made contact. In short, new human species could result from interstellar travel. While this would probably require separations of many thousands of years, it would almost certainly occur much more rapidly than it would under conditions of isolation on the Earth. Other environmental conditions would result in quite different changes to human populations. A colony isolated on a low-G planet, one with a surface gravity of say 0.75 G, would be exposed to a reduced stress from gravity, but it might also be exposed to a reduced pressure of oxygen in the atmosphere. Selection processes might therefore favor those individuals having more efficient respiratory systems and possibly those having larger rib cages, lungs and respiratory intake. Under less stringent gravitational stresses, those with slender physiques would have no great disadvantage, and any changes in the composition of the population with respect to body type would probably depend on other factors. On a small planet having a thinner atmosphere and probably a weaker magnetic field than the Earth, the normal background radiation level might well be substantially higher than that at the Earth's sea level for two reasons. First, as a result of less intense gravitational fractionation of rocky materials in the body of the planet during the formation period, the proportion of heavy minerals including radioactive materials in the crust might be higher. Second, with less shielding from cosmic ray particles from outer space, because of the thinner atmosphere and weaker magnetic field, there would be a greater influx of energetic particles from outside. Accordingly, mutation rates would be expected to be higher and possibly evolution would proceed at an accelerated rate. Even without genetic or muscular changes, human capabilities for physical action would be markedly changed on planets having gravitational accelerations different from the Earth's. This may be illustrated with reference to track and field records and various athletic events. For events such as the shot put, the javelin throw and the discus throw, the maximum mark attained would vary inversely with the G level. If a champion athlete can throw a javelin 281 feet on the Earth, for example, he could throw it about 375 feet on a planet with 0.75 G and only 187 feet on a 1.5 G planet. For the high jump, the relationship is not as simple, because though a man must lift his own center of mass about a foot above the recorded height of the bar, yet his center of mass is already about 3 feet above the ground when he starts his spring into the air. Taking this into account, we can calculate that if 5.5 feet is the standing high jump record on the Earth, it would be 7.1 feet on a 0.75 G planet and 3.8 feet on a 1.5 G planet. For running events, the relationships are still less clear, although it may be seen intuitively that men could run faster on low G planets and more slowly on high G planets than they can on the Earth's surface. Finally, the development of modified species of humanity will inevitably broaden the concept of a habitable planet. A human species modified by and acclimated to a 1.5 G planet will, in estimating the habitability of other planets, feel it possible to endure a 1.75 G planet which we could not. The human species modified by and acclimated to a 0.75 G planet and its thin atmosphere would be able to stretch a point toward further loss of G where we could not. The limits cannot be stretched forever, of course, for it is not likely, for instance, that by gradual acclimatization to lighter and lighter gravities human beings could ever adapt themselves to a planet so small as to have no atmosphere. Nevertheless, the galaxy might well in the end be inhabited by varieties of men who are not only of separate species but whose criteria of habitability in planets may not be the same.